being present here. I'm Pratyush from Delhi Technological University, and I'm gonna present our research titled Inverse Airfoil Design using Deep Learning. So here's the plan of our presentation. So as we know, airfoils are crucial components of many wind turbines, air vehicles, and high-speed aircrafts. And rapid design of required airfoils is very important in MS sections is difficult and time-consuming process requiring numerous design optimizations. But deep learning models such as CAEs and MLPs propose a promising alternative since they significantly reduce the computation time and power. By training the models with data generated using Java foil, the models can generate new airfoils that correspond to previously unseen design parameters. The use of CAEs further reduces the computation time and power, and thus enables us to predict airfoils at various angles of attack corresponding to design parameters such as Reynolds number, coefficient of lift, drag, moment, and pressure. So as explained earlier, airfoil are the crucial components in air vehicles, turbines, and high-speed aircraft. And design of airfoil is important in order to achieve a high lift-to-drag ratio. So trained deep learning models can significantly reduce the time required for computations, since multiple set of parameters can be predicted instantaneously. So earlier, many researchers have been used, have used the forward modeling technique. The modeling technique involves knowing an airfoil prior and then predicting the coefficients by simulations, such as CFD simulations and or maybe the machine learning prediction method. But inverse airfoil design methodology is less studied, and it involves using the parameters problems with genetic and like curve fitting methods is that they are they require to run the entire set of the entire process for a single set of design parameters and is much time consuming. And also they are less flexible in modeling complex functions. But on the other hand, our method of using deep learning based on the universal approximation theorem can approximate any continuous function and moreover can produce results for multiple set of parameters. So here's the dataset that have been used for training the model. So for the autoencoder, 2D images of the airfoils with dimension 200 cross 500 were used as both input and output. And for the MLPs, these were the design parameters which are used as the input, and the corresponding latent vector produced by the trained encoder model is used as the output. And for testing, unseen design parameters which were not used for training are given to the trained MLP model, which is then decoded or reconstructed by the trained decoder to produce the airfoil. So the so finally, for a training, testing, and validation, we have used a ratio of 80:10:10. So here's our CAE model. So a convolutional autoencoder model. So basically, an autoencoder model consists of an encoder and a decoder. The encoder takes the input 2D matrix or airfoil image and compresses it to a single latent space of dimension Z, and then it is reshaped or reconstructed using a decoder into the airfoil image. So this way, the entire information of the airfoil, which was in dimension 200 cross 500, will now be represented in only 12 dimensions. So this, as mentioned earlier, heavily reduces the computation time required and also enables the mapping of the design parameters to that latent vector of an airfoil using this MLP architecture. So this multi-layer perceptron model consists of 4 layers, so it is quite light as well, of dimensions 16, 32, 64, and 32. So these are the results of the training, validation, and loss graphs for both. This is for the autoencoder and the right one is for the MLP. As we can see, in both training and validation, we have good convergence. And these are some of the results of airfoils that we have produced. So we passed in the 5 design parameters mentioned, produced the predicted latent space, and then that predicted latent space was decoded or reconstructed using an airfoil. So here is the ground truth and the prediction. And here is the ground truth and the prediction for the 2 samples. In the first sample, we can see we have high thickness and low angle of attack. In the second sample, we can see we have small thickness and high angle of attack. So basically, our model produces accurate results for high Reynolds number for all sets of Reynolds number, and as well as for all Reynolds number for high thickness and for all sets of camber as well. But we noticed that for very high camber, the model actually degrades a bit because due to lack of such samples in the training set. And like this is basically the frequency distribution of error plots. And we can see that the majority of the testing samples produced an error of 0.02. And so that becomes the mean. So what are the limitations of our current research? Currently, our model only produces a one-to-one mapping, i.e. for a single set of design parameters, only a single airfoil with a specific angle of attack is generated. So to address this limitation in the future studies, what we can do is we can use variational and generative deep learning models, which will produce multiple outputs for a single given design parameter. Additionally, we can augment our training dataset in order to improve many more samples with high camber so that our accuracy increases there as well. And that's it. These were the references that we have used in our study. Thank you.
Yash Kumar from Delhi Technological University. Sir, I'm presenting my slides for the paper named Predictive Analysis of Inverse Convection Optimal Control Problem. So abstract. So we have considered the inverse convection problem in which the problems aim to recover the boundary wall flux using measurements of thermocouples placed in the fluid. We consider the case of convection by fully developed flow. So the steady state elliptical energy equation governs the constraint of the problem. So we use multiple examples of wall heat flux and approaches used are able to predict the original flux with high accuracy. We compare the predictive heat flux using Lagrange multiplier and conjugate gradient method in case of curve measurements. So intro. Applications of such problems are determining the surface temperature of spacecraft and measuring temperature in glass production. Also calculating heat transfer and radiative properties in unfavorable conditions like erosion, extreme temperature, or sublimation. So what is an optimal control problem? It includes a cost functional that is a function of state and control variables. So the aim of the problem is to determine control and state variable that minimizes cost function. Research gap. So inverse convection issue has not received as much attention as inverse heat conduction problem because they are mathematically more challenging. Also, effect of noisy measurements on results of optimal control problem is not studied for flow inside the duct. So thus we study the effect of noise in measurement on methods such as Lagrange multiplier and conjugate gradient method. We compare them based on the error in prediction under corrupt data. So problem statement. First I describe the direct problem in which we are. So this is our domain, which consists of a duct formed by parallel plates. The flow inside the duct is considered laminar and fully developed. In this domain, we show the boundary conditions such as control boundary condition, Dirichlet boundary, and Newman boundary condition. The black dots shown in the images are the thermocouples on which the measurement is taken, and there is a fluid flow between the plates. So in the direct problem, we are given the boundary conditions and the governing equations through which we have to solve for T, that is the temperature of the fluid. So we consider the case of small Pachelet number, and aim of our direct problem is to find the steady state temperature distribution of the fluid using the given boundary conditions. Inverse problem. In the inverse problem, boundary heat flux is known, and we are given the temperature. We are given the temperature measurement at the location of thermocouples in the fluid. So we have to minimize this cost functional, which is denoted by J. And so the finite element approximation of the problem is mentioned down here. So methodology. So the first method that we are using is the Lagrange multiplier method. So it consists of Lagrange function that is denoted by L. The solution of unconstrained minimization problem for the Lagrange function is also the solution to the constrained minimization of the cost function. So after After using finite element approximation, we can see the matrix that is formed by that is formed. So the second method that we are using is the conjugate gradient method. It is an iterative process, and the flux of in the next step is computed using the given formula. So where beta is the step size and r is the descent direction, which is based upon the information of gradient of the j results. So the first image shows the solution of the direct problem using the boundary conditions, and using the solution of the direct problems, we compute the solution of the inverse problem using CGM and the LLM method. And in the last image, we have shown the boundary heat flux that we have taken, and that is predicted by the inverse solution. So we can see a pretty good overlap between the two. So now we compare them with using noisy measurements. So we added white Gaussian noise to the measurements. So we can see at SNR 60 the percentage error of Lagrange multiplier method was 7.22 and CGM was 1.68. And when we increase the noise to SNR 50, we can see the error percentage of Lagrange multiplier method increased to 17.66, but the error percentage of CGM method remained the same. This is example two for a experiment. In this, the original function is sine function, and we can see the percentage error of LMM method is 4.65 and CGM method is 1.68 at an SNR 60. After increasing the noise in the measurement, we can see the error percentage in the Lagrange multiplier method has increased, but the percentage error in CGM method has not increased that much. Conclusion. We have solved the problem of finding boundary flux in a duct with fully developed flow using measurements of thermocouples. We have used two methods, namely Lagrange multiplier method and the conjugate gradient method, to solve the problem. We have considered the case of small Pachelet number, and through the result, we can see that even in corrupt measurements, the prediction of CGM method is better than those of the LLM method. These are the references.